Hello, everyone. Welcome back to Manufacturing Matters, a podcast where we talk about the trends and technologies shaping global industry and logistics and other sectors of the economy. I'm Dan McCarthy of Tech B2B Marketing. Joining me today are my colleague Aaron Hand. Say hi, Aaron.
Howdy.
Wolf, Wolfgang Sauter, Senior Distinguished Engineer at Marvell Technology. We're delighted to have him here today because Marvell is a big player in the area of semiconductors as well as data centers. And we have a lot to talk about today, a lot to ground to cover. So welcome to the podcast, Wolfgang. Thanks for joining us.
Great. Thanks for the welcome.
Before we kick off and get into the deep dive into the technology, could just start off by telling us a little bit about Marvell Technology, what it does, where it fits into the semiconductor space, and what you do.
Okay, good. Yeah. So I'm a packaging guy. Let's start there, and let me first go to the company and then come back to what do I do. So Marvell is a fabless semiconductor company. We focus on what we call data infrastructure products. We don't make consumer products. So for some of your listening audience, Marvell may potentially be a less known name just because you don't see it on the street. You don't carry devices around that carry our brand. But our chips go into the data centers, into all the places where the data that comes from your devices routes through, gets stored, gets processed, etc. So kind of in the buildings that you don't see. So that's why it's not such a street name, but it's a pretty well-known name and a big player in the custom chip design for AI, for data center and other infrastructure aspects. Now, I did just mention custom. So coming back around to what do I do? What does my team do? We are a fairly small team of technologists, and we cover the entire spectrum of a chip lifecycle. So if you think about a chip from beginning to end, there's architecture, there's IP, there's packaging, there's quality, there's yield, there's manufacturing, a lot of different aspects. And so our team covers all of these aspects with experts from all disciplines. And we are kind of the first front of the company when we talk to our data center customers. So we work a lot directly with these customers on what is it they need for the next generation, which direction is the industry going, and then also bringing that back into the company, aligning Marvell's roadmap for the technology. What do we need for IP development? What do we need for technology development? And driving that so that our roadmap for the next 2 to 5 years lines up with what our customers need and having a superior solution for our customers.
Great. Well, we're talking to the right guy on trends and technology. I know what you do expands beyond the data center, but I wanted to actually focus a little bit on that first because I know there's some developments there in packaging that I think are particularly interesting. But before we do, just a little bit of context for our listeners. You get a lot of trends demanding more bandwidth in the data center. You have AI, crypto, all these things are pushing for more bandwidth in the data center. And a lot of that comes down to streamlining the electrical and optical conversions within the pluggable transceivers that connect the thousands of servers and switches in those data centers. Streamlining that comes down to how those electrical and optical functions are packaged, right? So that's why we're talking to you today. Maybe you could take it from there and explain or provide us some context on why next generation chip packaging is so critical to pushing or enabling the push to 1.6 terabyte transceivers.
Okay, good. And if I may, maybe I can rewind us a little bit and step back a little bit. You mentioned very specifically the 1.6T transceiver. And I first want to kind of separate the different areas of interconnect and where the bandwidth that you just mentioned may be needed. So there's bandwidth in the data center that you kind of see, right? You look in a data center, there's all these black cabinets full of cables, thousands of cables coming out. So that is where we talk about the transceivers. So they connect rack to rack and tray to tray in a data center. So that's very visible. That's kind of what you maybe think about as the interconnect. But then there's also a very different type of bandwidth discussion, and that is inside the package. So if you go inside a tray, you go inside the XPU, And inside the XPU, there's pretty much never today just one chip in there. There's always several chips, including memories in there. And there's tremendous bandwidth requirement, how much data you have to push around from one chip to the next chip within the package. So I'm sure we come back to the whole chiplet discussion later in this podcast.
Okay.
But I wanted to first differentiate a little bit. There's these two very, very separate areas. The one that you see when you walk in a data center, and then there's the other one that you don't really see because it's inside a tray, inside a package, and that is really generally referred to as advanced packaging. So most of what we do is happening inside that. Now, if we want to go a little bit into the 1.6T, that is obviously a very, very challenging part. It's a sub-discipline, I want to say, of advanced packaging. And it's really challenging in many, many different ways. It is a very small form factor. It has thermal challenges. The data rate goes up every generation. It pretty much doubles every generation. Right? It was 400, now it's 800. It's 1.6T in development. All of these drive advanced packaging by itself, but it's again very customized, small element. With the challenges really being very small form factor, very precise alignment of fibers, thermal management, and then how do you contain all of these challenges in this very, very small form factor.
Right.
Now, if we think about going forward, how does that intersect maybe the bigger scope of advanced packaging and the XPU? There's a lot of discussion about co-package optics, and that would then move the transceiver from where you see it today, right, the back plane or the front plane, where you see the cables coming out, move it from there to inside the tray and right onto the package where the XPU sits. And that's then called co-package optics, when you move the optics onto the package. And that has additional power benefits if it's used in the right way.
So yeah, Wolfgang, one of the things I wanted to kind of pull back a little further too, and take a look at some of the packaging options that are out there, and how these, you mentioned about how most chips have multiple chips inside them. I have been hearing a lot about chiplets in general, which is the general idea being that you're not printing all of those semiconductor lines just on one die. You've got multiple die within that package. So maybe you could kind of talk a bit about that idea of chiplets and explain the advantages of having multiple die within that package.
Okay, yeah, sure. And want to again make sure let's talk about the XPU first, because that's really where most of it is happening. And if you were to be able to see inside a data center, inside a tray, you would and open up the module, you would see that there's today several chips in there, including memories. Right? It's even today, and one or more of these chips will actually be the compute die. And that is kind of the interesting part, is an architect of a XPU will always fill up the reticle, right? That's just what architects do. If you can make something on one chip, you will.
Okay.
The problem is if you can't, right? And that's the world we're in today. You can't fit all the content anymore into one single reticle, which means you need more than one chip. So chiplets is, I would say, in that perspective, less driven out of opportunity, but out of necessity. You just can't build it any other way. If you were to sum up all the content that's in one of these XPUs, including all the memory and the DRAM die, you have an area that's probably about this big, and it's gigantic. So there is one part of chiplets that is, as I described, architects will always fill up the chiplet or the main die, the compute die. So from a yield or cost perspective, that doesn't really improve anything, right? Because you are filling up the reticle, you're going to drive that to 2 nanometer or beyond in the most advanced node. So the yield is going to be absolutely awful on that thing, always, right? And that's because the architects want to stay on a monolithic die. Now, the other part of it is all the other functions. So let's say everything else that is not compute, that is the content you will shift onto surrounding chiplets. So for example, I/O. And the parts, those will benefit from being smaller, right? So there is a yield and cost benefit in that aspect. There's also the additional benefit that you've now become flexible. You don't have to build that chiplet in the same technology node anymore. You can build that in a previous technology node. So again, cost reduction opportunity. So you combine a 2 nanometer compute die with a 3 or 5 nanometer I/O die. And the other advantage, and that's probably the biggest advantage, is a time to market advantage. Because as you develop technology, one of the longest poles is IP development. How do you communicate all the I/O, long reach SerDes, very high speed SerDes? Takes a long time to develop and to qualify. And if you can use an existing chiplet in an older node that you've already qualified, that doesn't scale well anyway to newer nodes, you have a huge advantage in time to market. So that's really the chiplet advantage. Less opportunistic, as it's often described in the industry, but a necessity, and you use it where it really provides value.
Does that introduce more manufacturing challenges versus today's packaging?
Well, I would say today we're there already. But if you compare it to yesterday's packaging, you had one chip in one package. Very, very simple. Very simple. Today you have several chips in one package that generally need to be integrated on an interposer 2.5D solution. Significantly more complex and very, very expensive.
Okay. You mentioned interposers. Marvell recently launched a new interposer platform that packs a lot of functionality into that semiconductor package. I'm going to let you summarize the details, but my question is whether the primary driver for that was based on improving pluggable or overall chip performance, or was it just smoothing the manufacturing challenges on chiplet packaging, or both? What was the driver there?
It's really an ecosystem question.
Okay.
So if you look at today's manufacturing environment, you have a clear leader out there, and then all the OSATs that have historically been the companies who package the products are kind of on the sideline watching, right?
Okay.
And so we've partnered with multiple of them to bring them up to a level where we can use them on the XPU products and establish an ecosystem that is sufficient to address some of the market at least. I think the industry leaders will remain leaders because as you bring up kind of the second, third source suppliers, the leaders will always march ahead and create the next offering and continue to be in the lead. So there'll always be a first adopter and then the follow-up ecosystem.
So, but to tell us a little bit more about that technology, is it the interposer? Is that what you're defining as the ecosystem, or is?
Yeah, exactly. Yeah.
Okay.
Yeah. So to connect these chips together, and that's where we come back around to what I said in the beginning, the advanced packaging is really happening inside the XPU. So you have multiple, reticle size die with some I/O die and high bandwidth memories. And the interconnect between them requires such high bandwidth that you need thousands of wires, sometimes tens of thousands of wires to connect these together. And the only way to connect them together is with very, very fine lines and spaces. So a typical package could never do that. So you need something that's built in a fab-like environment that can build, 2-micron line space over 7, 8 layers to connect them all together.
Okay. And does this also accommodate any of the optical connections? Would this qualify as co-packaged optics, or is this a separate?
Yeah, it's a little bit separate. Generally, the optical components may go go straight to a 3D type integration rather than 2.5D integration. There isn't a one thing solves all problems. I think but for like the 2.5D integration is really for a large area integration. If you have a lot of components that you need to span a large area for, versus 3D is more you have a very space constrained environment, and you just can't grow out of that. You need to grow in the vertical rather than horizontal.
Yeah, and I did want to get into that a bit too, about kind of the differences between 3D packaging, for example, and 2.5D. So 3D is really stacking die on top of each other, and then you have to have those interconnects with through silicon vias or bumps to make those connections, correct? Whereas 2.5D spreads more horizontally.
Yeah, that is correct. Yeah.
Okay. So what I mean, 3D is really out of necessity, right? If you don't have the space to spread horizontally, are there other advantages for going to a 3D package?
There is, yeah. You can because the interconnect pitch in a 3D orientation is much denser than a 2.5D, and it's also much shorter. So you essentially a 3D die acts almost like a single die, right? So you can take where I started earlier. Architects always want to stay within one chip if they can. So now you essentially build two chips in the size of one, because you have this incredible interconnectivity between those two chips. It is, however, very complex to do 3D. We've already taped out our first multi-core processor in a 3D fashion recently. And we learned a lot through it. It's very difficult, and you have to prepare for it for a long time, because you really have to think about it. The 3D today, true 3D, right? True 3D meaning it's hybrid bonded, and it's in a face-to-face configuration, meaning an active side of a die faces another active side of a die.
Right.
And then the bottom die that is now face up, so it's flipped up from what it was previously. That usually active side was down, now active side is up. You have to think about, as you develop the IP, how do you escape signals from the bottom die? Because they can't just come out anymore as they did before. They actually have to go through the silicon before they can escape. So all of your IP, as you develop the IP, needs to consider that, and that space for the TSVs and that escape has to be built in as you develop the IP, which, as I mentioned before, is always the long pole in the tent, right? So you know, years before you actually want to use it on a product, you have to lay out your IP already considering that.
Yeah, which frankly, all of this stuff just absolutely fascinates me. The amount of complexity that you're dealing with, and the solutions that engineers have come up with and designers have come up with just to solve all these issues. Just the sheer complexity, I think, is a big enough issue. But then, are you also dealing with other ramifications of that? Are there heat dissipation problems, for example?
Yeah. No, great question. Absolutely. Thermal has always been considered the biggest challenge for 3D design. And thermal is challenging today, right? Even in a 2.5D configuration, it's really challenging to cool these chips, next generation chips. We expect or modules to be in the 4 kilowatt range. It's absolutely incredible. And then you have several of those in one tray. So cooling that is an absolute masterpiece, really. And now you want to double that essentially by stacking them on top of each other in the same geometry, right? You have twice as much power if you were to stack compute on top of compute. That just can't be cool anymore. So you have to be very careful as you consider 3D. How do you architect so that you don't stack something high power on top of something else that's high power? It just won't work. And it won't work for two reasons. One is thermal, so power out, but the other one is power in. How do you get enough power in without burning up your interconnects?
Wow.
The 3D chip that you're taping out now, or is the application, the target application for that? Is that data center, or is it another sector?
It's a processor. Yeah. It's not a full-blown product that will go into production, but it's our first prototype of a
Sure.
processor in 3D, and it's very carefully architected so that one layer has compute and the other layer has lower power in that area.
Okay.
So you talk about lessons learned there. Are there, can you give examples of somewhere, maybe a direction you've gone and you say, nope, that's not going to work. We're going to back up and come at this from a different angle?
I think there were certainly many lessons learned along the way. I think none of them have been completely revolutionary. So I don't think there's any fundamental shift in how we approach things. So I think we planned fairly well for it, and it's in the fab. So maybe ask me again in 6 months. So.
Great. So then I guess get into the 2.5D aspects, and this is where your interposer platform fits in. Is that right?
That is correct. Yeah.
Okay. So where do you see the trade-offs there? How is that 2.5D technology working for you, and what are the challenges and advantages there?
Yeah. So 2.5D, if we just rewind 10 years ago, right, it didn't exist essentially. It was when we were IBM at the time, and we had a product in 2.5D, but it was incredibly complicated. It was incredibly expensive. It wasn't mainstream. And now if you go to today, it is a mainstream technology. Every single GPU out there, XPU, is 2.5D. Every product that has an HBM memory is 2.5D. It really has become mainstream technology. There is what I mentioned before, that challenge of early adopter and the early technology availability. As we build these systems bigger and bigger and bigger, it's very, very challenging to develop 2.5D solutions that can be so large and still assemble them onto an organic substrate. Right? And that's kind of the big challenge, is how can we accelerate getting them up proactively to the sizes we'll need, not just the generation we're building now, but the generation afterwards and after that.
Okay.
Are there other package types that should be on our radar? Fan-out wafer level packaging, for example, or hybrid bonding. You talked about a little bit. Silicon bridges. I know it goes on and on, but I mean, in terms of what Marvell's working on, do you see any demand drivers? These are unique solutions.
Yeah. We always have to be looking out for all of these technologies. I would say, if you mentioned silicon bridges, for example, so that is also a 2.5D technology, right? EMIB uses silicon bridges. Same with wafer level fan out. It's just not processed on silicon; it's processed on an organic basis. So they're all pretty similar. What I would say maybe is we're monitoring all of those, and we have to. But really, I think the packaging technologies we have to look out for are the ones we don't know yet. And what is the next game changer?
Right.
And
right.
Yeah.
Is and we're just gonna jump back into co-packaged optics. Is that? I mean, I know that it's gotten a lot of hype, and I use that term politely. But is it? Do you see that as a future area where you really need to invest? Is it something you sort of need to keep your eye on?
Co-packaged optics?
Yeah.
Absolutely, 100%.
Okay.
Yeah. No, we have co-packaged optics technology, and it will come. Again, kind of rewinding back to where we started this discussion, there's electrical interconnect and there's optical interconnect, and there will always be a need for both, and the crossover point will shift over time, and that's just a function of signal speed.
Let me ask. Go ahead. I'm sorry.
Yeah. And so today we can reach, within a tray for sure, but then also tray to tray, or within a rack probably, for the most part electrically. But as we go to 200 gig instead of 100 gig, and then to 400 gig instead of 200 gig, every time you double speed of your interconnect, you will only get half the distance if you go electrical.
Right.
So that crossover point towards CPO will shift over time. And You will
Okay.
you will never be 100% in optical, right? Because if you go very short distance, you burn extra power. If you don't need a repeater, you burn extra power and you add extra cost and reliability concerns. So you will never be all optical, but at the same time, you will also never be all electrical because you can't get to the distance.
Okay.
They'll coexist.
Where is it today, the COPA, in terms of the architecture of the tray in co-packaged optics? I mean, is it penetrating deeper toward the core silicon in the chips, or is it good large lights still around the perimeter?
Yeah, it's still on the perimeter. It won't make it onto a 2 nanometer compute die, right? So it'll escape the compute complex you want, and then you can drive either directly from an I/O chiplet into a co-packaged optics solution, or have some type of redriver in the CPO component itself.
Okay, and you talked a little bit about you're going to need optics, but it'll not be entirely optical solution. So the question is, I think, for a lot of people, is how quickly this is going to advance, how quickly it's capable of advancing in terms of the manufacturing scalability, which prompted some thinking around it. I know some analysts are talking about seeing a renaissance in copper-based solutions like direct copper attachments, active electrical cables. Do you see that as slowing the progression of co-packaged optics down, or replacing, complementing?
I think it's really complementing. So we actually do a ton of work on CPC, so co-packaged copper, moving copper connectors onto the package.
Okay.
I don't think that will necessarily delay or compete with the CPO, because again, there'll be both electrical and optical, and
Sure.
it just depends on the reach of how far you need to go. So they'll coexist, and the crossover point will continue to shift as we go up in speed.
It's just very interesting to me just to see, which solution do we use, and the answer is yes, right?
Yes.
Everything has to come together and work together. All of these trade-offs and consequences, and I think about the days. I used to cover semiconductor manufacturing regularly for a good 12 years, but in those days, the package was just the plastic box around the die, and wasn't,
Right.
it was just a protective and interconnect issue, and things have changed a ton since then. So that package is just so instrumental in getting the performance you need. And so I feel the need, at least for my brain, to back up here, and let's look at those data centers and think about what your goals are there and how that package is affecting those goals. So sorry, I'm coming at this kind of in a roundabout way, but I'm looking at, compute density, thermal issues, and data centers being so energy intensive, power hungry. What does packaging affect all of those, or where do you contribute, I guess?
Yeah, they affect absolutely all of them. Actually, if we kind of think about all the words we used in this conversation, right? We talked about 3D, we talked about die-to-die, interfaces, partitioning, CPC, CPO, hybrid bonding. All of these are in the bucket packaging, right? And I mean, some of them are actually fab-based, so you can kind of argue, are they
Right.
fab, are they chip, are they package? It all becomes just one. But I think in our traditional use of the words and the languages, you would probably say that all of these changes are packaging, or at least integration driven. So I think we've reached a point where packaging/integration really drives chip design, and to a certain degree also system design today, and becomes really the heart of the whole system.
So are you able through packaging to help with the energy issue in data centers?
I think a lot of that. So if we take the die-to-die interconnect, I mentioned we need incredible amount of bandwidth between the compute die, right, or the compute to the I/O die, or compute to the memory, and that is a very significant portion of the energy burned. And optimizing that die to die is absolutely critical for these applications. So that's where we have probably the industry best die to die interface right now, and continuing to build on that, because it is one of the biggest levers we have.
Okay.
I'm curious. I know that packaging has become much more of an expense in the overall production. Is manufacturing? Is that because of the manufacturing of chips, of chip packaging today? Is that where most of those costs come from, or is it more in the testing, other phases of production?
No, it's really in the production, and I'm not sure that it's all cost driven, or to a large degree also price driven.
Right.
And so if you say, historically, maybe packaging could have accounted for maybe 20% of the product cost. We've seen now cases where it's like 40 to 50% of the product cost. It's absolutely fascinating what happened there. In terms of kind of, I think you're hinting towards kind of also the ecosystem and the industry and how do you work with them, and that has completely changed. If you again go back in time, probably only 5 years, the relationship between a customer with an OSAT was to beat them up every quarter at the QBR and squeeze every last penny out of them. And that relationship has completely changed. Today, for the most part, I mentioned we have these very highly customized solutions, and oftentimes not more than one supplier who can develop that particular solution. You need to come in with a very, very different approach. You have to treat that as a partner relationship. You either both win or you both lose.
Right.
But it requires a very different skill set, a very different approach, a very different business environment to compared to 5 years ago.
Yeah. On that note, I mean, this is a very collaborative industry, much more than a lot of industries. It's a lot of inputs globally. So I guess I'm asking a very broad question. Are there emerging bottlenecks from the supply chain that are shaping the direction, or are likely to shape the direction of advanced packaging?
I don't think any new ones compared to what we've had in the last 2-3 years. But we're already pretty tight, right? Because there isn't the copy exact we had on previous technologies. We are in these very, very highly customized solutions that you get from one supplier. They go through these incredible ramps up, and it's only a 2-year, 3-year production cycle. So there isn't really time to develop many alternative technologies and solutions. There's a very high level of codependence on being successful. So that is the biggest challenge for the.
Okay, the codependence.
Yeah. Yep.
Okay, is that landscape likely to change if the uncertainty around supply chains lasts longer, or is it sort of? I mean, is it a generational thing where the next generation we have to reinvent you're reinventing it now, right? I mean, you're developing all those technologies now. So I guess I'm curious with the uncertainty. How do you plan ahead for the next phase of advanced packaging when the supply chain is so uncertain?
Yeah. I mean, and I'll be just very, very direct, right? It's TSMC is in the lead, and they will always, if you have a product that has to ramp incredibly fast and only has a 2 or 3 year life cycle, it's extremely high volumes. It's very hard to get around that as the default option.
Okay.
Intel is developing some very interesting technologies as well, or has developed and now optimizing that technology that could become very, very interesting. And then kind of all the other OSATs are always this half step behind that makes it really hard for them to catch, the ramp initially, but they could come in at the tail end of the production cycle. And that's how it works today.
So this is very dense, very complicated topic. So let me ask a broad question. Is there anything we could expect further down the road for advanced packaging? What's next? Is there anything we haven't covered, I suppose, that we probably should have? What are you excited about?
There's a ton of different things, and it goes in all directions. So we mentioned co-packaged copper a little bit, right? So that itself drives a lot of complexity on, now all of a sudden you have cables coming out of a package. Now, how do you route them in a tray and in a rack, and how do you connect them? How do you test them? How do you do reliability, etc.? I think a different topic is integrated voltage regulator. Today, the voltage regulators sit on the board, but that has some challenges of delivering power to the package. It would actually be much better if the voltage regulators were directly on the package. And that will happen also. We're doing a lot of work in that space. Made a recent announcement also with several partners. And once you do all that, once you get your electrical signals off the package and cables, you get your power conversion directly on the package, and then you look at your board and what's left. There's like almost nothing left on the board.
Right.
So I think that's probably the most exciting view of how does the package take over more and more. Like we said, it takes over a lot more and more of the fab processing, and now how do we go the other direction? How do we take over more and more of the whole system and system board aspect? So
Right.
I think that's the really exciting part about packaging, that it grows in both directions very, very fast.
Sure.
Wow.
Well, we could go on on this topic. I wish we could. I don't want to take more of your time, but this has been a fascinating conversation. Is there anything else that we haven't covered that before we go? We've covered CPO, active electronic cables. I think we opened another can of worms. We could be here all day. So, Wolfgang, it's been a fascinating conversation with you. I'm going to give you a big thank you to you and Marvell for joining us today. Listeners, if you have any questions for Wolfgang, please feel free to post them in the LinkedIn thread for this podcast. If you're interested in past episodes of Manufacturing Matters, you can find them on our website, manufacturing-matters.com, or your favorite podcast platform. And for anyone wishing to be in the loop on upcoming conversations about automation, please follow us on LinkedIn. And one more thank you to Wolfgang for joining us today. Really appreciate your time. And thank you all for joining us.
Thank you. Great conversation.
Thanks.